morning. So in the last couple of lectures, we have tried to see the solutions in a very generalized setup in a Hilbert space thing. And we also seen examples of minimization problem and leading to a formulation weaker than the Laplace equation. So Laplace equation in a classical sense we have studied throughout this course, but quite often the physical solutions are not captured by the PDE, rather another formulation which is called a weak formulation. In the process of explaining that, what we have seen, we have introduced a completion of C1 naught of omega bar is equal to completion as x equal to leading to a v in L2 of omega such that your dv by dxi is also in L2 of omega with v equal to 0 on d omega. So the issue which we have not understood this space properly, what is the meaning of this meaning? Meaning has to be interpreted in a weaker sense. So as I said earlier, in a weak sense. As I said earlier, this was the beginning of end of the 19th century and the beginning of the 20th century. Finally, a stable foundation was given by Lawrence Storrs. Stable foundation mathematically by Lawrence Storrs in 1940s, maybe 1944, and introduced theory of distributions. So the earlier, prior to this, the distribution not only helped in understanding VDEs in a weaker sense, it also helped in understanding other physics like the Dirac delta and its derivative. Dirac introduced in the 1920s and 30s Dirac delta and its derivatives, because these are all some objects, its derivatives. And Dirac was using the symbolic calculus. So it's unified all these calculus. And it unified the physics and other things doing in a very symbolic way without having a proper mathematical foundation, was justified by the theory of distributions. And after 1940s, in the last 70 years or so, the theory of the PDE has the study of PDE has completely changed. Study of PDE completely changed, and it became a topic of function, and it became a topic of functional analysis, a topic of functional analysis, if you want it. So the modern and so together with the abstract development of functional analysis helped to study PDE together with this theory. So what we are going to see in a couple of lectures or something, a glimpse of, we see only a glimpse of distribution theory. Not that, because that needs, if you want to understand it properly, you need at least a 1 semester full course, and that's what I said, it will be an advanced PDE if there is a new course on that one. But we try to give these processes. Okay, so we want to give a glimpse of distribution theory. Okay. So we want to try to understand. So let me motivate you first. Motivation. Quite often, a function x going to f of x represents a physical quantity. Say temperature represents a physical quantity. Okay. And what's interesting is that you cannot measure. X is a mathematical concept, right? A point is a mathematical concept, and no physical quantity can be exactly measured. Exact measurement of fx is not possible. Exact measurement at a point is not possible experimentally. At a point, x is not possible at a point. So what we get basically is some average. What we get are averages around a point, or averages around a point. That's all you can measure. Say suppose you are measuring the temperature at a point with an instrument. You will not be measuring exactly at a point. You basically get an average around that. So if you have a domain here, so basically if you have a point here, so if you look at a neighborhood U, this is X. So the objects available are basically objects are not f of x actual physically, but integral of f of x dx over the neighborhood. Okay, for that neighborhood. So but then when the u is close enough, so most of the time when u is small, then the question is that is this average, you take an average if you want, is close to your, so let me fix a point x naught. So you are averaging about, so you have a point x naught. Okay, so you are fixing is this close to f of x naught. So let's look at an example. Suppose f is from AB to R continuous. Continuous. And then, maybe I will take very precisely example. Say minus 1 to 1. And want to compute f of 0. Compute f of 0. So instead of f of 0, what may be available is a neighborhood. Minus h2, minus h2, h, f of t, dt. This you know, if f is continuous, this will converge to f of 0. So, and these are the objects available. These are the experimental objects available. Objects by experiments, basically. This is one way of motivating, that's okay. But so, if f is not continuous, if f is not continuous at 0, this may not represent f of 0, may not represent f of 0. So we need to work with these objects. So we need to work with objects of type, in general I am writing objects of type integral u f of x for all open U in omega. Open or closed doesn't matter now. For the motivation is number. So these are the objects to work with, because the averages, if you consider here, may not represent that. This is true even in higher dimension. If f is a continuous function, so if you take a point and if you take a neighborhood u, so if you calculate if x naught here, so if f of x our neighborhood averages, this will go to f of x naught if f is only continuous. So you need smoothness. If there is no smoothness, and your physical quantities may not be smooth all the time, your physical things can exhibit singularities. So on a singular function, if you try to work with f of x naught point-wise, may not yield the correct result or may not produce the correct solutions. So you have to work with these objects. So if we write u f of x dx, I can write this by taking it as a characteristic function f of x, characteristic function of u of x dx. So there are two difficulties now. Difficulties if you work with these sets. Difficulties. One difficulty, you want to deal with f not smooth. Deal with f not smooth. Therefore, when you interact something, you need, this indicates you need smoothness here. Smoothness for that function. Smoothness require. Otherwise, both are bad. These objects will be very bad. Require smoothness. The best smoothness possible. See infinity. But chi-u is also not smooth. The characteristic function chi-u is not smooth. Okay. So that indicates. And second thing, you want a localization. I will tell you, because you want to find the value approximately here. So you want to integrate over smaller and smaller neighborhoods. This is called typically a localization problem. Localization. In mathematically, this is handled by looking at compactly supported functions. You will see more precisely looking at compactly supported functions. Supported functions. So instead of looking for all neighborhoods u, so this forced to consider a class of test functions, where class of test functions which we denote by d omega now is for a notation, because I will use this one. D omega is nothing but cc infinity. Right now it is cc infinity of omega. Later we put an appropriate topology. The set of all c infinity function, because you are set of all v c infinity functions with the support of v compact. And then try to consider, these are all intuitive motivations. So consider expressions of the form, expression or association of the form. Consider association phi going to integral of f for a given function. So basically we are getting out of the class of functions and making a bigger class of functions where phi for all. So this is from d omega to r of c, you see. So these are new objects. So every function, so we will state an immediate result. So we want to realize a every function f at is some integrable function not as a point-wise association, not as x going to f of x, but as an association phi going to. There are difficulties. That is where the whole theory you have to understand. But you have seen that. The thing is that this may produce new objects. So every function has a point-wise association. You are associating with an object. This is not a function. This is rather a functional, which you will see soon. But this may produce new objects. May produce new objects, which need not be coming from a function also. Okay, new objects. I will cut that. So let's try to first understand that more with a theorem we will understand that every function can be do this way. Uniquely can be done that. Because if you create one function is associating with something, end of it that new object not uniquely identify with this one. Suppose it identified two functions, then that may not be a good association. So here that is what is called the basically the localization. So let me do this localization now. So again, these are all initially I told you I am not going to develop theory and prove results. Rather, we want to understand things. So let f be continuous again. Okay, suppose f is continuous in AB. Is continuous on AB. So we will always see at continuity, derive the property, and then try to remove the smoothness. Let f be continuous in AB. Then this is a small exercise you should work out. If integral of f equal to 0, say from a to b, for all phi in d, that one c infinity, you don't need c infinity function, but we are it is enough for continuous functions. So, but compact support is important. Okay, d of ab, that implies f equal to 0. That means you can identify uniquely. For f is continuous, this is I will tell you a little more about it. The proof is easy, right? Proof, what do you do? So you just do this exercise. This is an important factor with this one. So a function can be completely recovered from this thing. That's a, so I will give symbolically, not symbolically, geometrically. Suppose you have a function like this and you have a point here, x0. So if fx0 is positive, you can find a neighborhood in such a way that on that neighborhood you take phi to be 1, and then such functions you can construct. So this is your 1, this is at 1. Okay, so this is at 1. So you take phi to be 1 here, something like that in that neighborhood. And this is a 1, you don't need 1. But what I am saying that you can easily prove that. So this will imply integral of, because there exists a neighborhood for which if fx not equal to 0 and if f is continuous, fx will be positive. This will imply fx will be positive in a neighborhood. And you are choosing phi also to be positive. So that will imply integral of f will be positive, which will be a contradiction. So I will make things clear. So you leave it as an exercise. So what does this immediately imply? This implies if f equal to g, if and only if integral of f phi equal to integral of f g phi for all phi in d omega. So that means integral of f phi uniquely determines f. That's what it shows. So you see, so this is so every function, so this basically implies that f is uniquely identified by integral of f phi. So this is uniquely identified. That means you can recover your function if you know by integral. If you know this integral of phi for all phi in d omega, then you can get back your f. In f is in there, some, as long as this is defined. But what I am saying that this association which we are going to do, and if f is not continuous or f is locally integrable, so there are more general result. So we can develop. You don't need you because you want to get out of that, right? Result integral of f is locally integrable. F is locally integrable, not continuous. Locally integrable, and integral of f equal, these are all in measure theory, you would have learned it, if equal to 0 for all phi in d omega, then that will imply f is 0 almost everywhere. So you will only get almost everywhere, and that's enough for these things. Okay, so this is how. So what we are going to see now, from now onwards, instead of x going to f of f, whenever this is possible, f is continuous, it's fine. Otherwise, we work with, and that's the basic motivation. Okay, phi going to integral of f phi. And with this, let's get a motivation for f prime. Okay, motivation for weak derivative. Okay, so let's see how things will work. Motivation for weak derivative with that. So suppose you will start with f is in. Suppose f from AB, okay, to R is smooth. Okay, you will see R is C1. So that mean f is continuous and f prime is continuous. We will do that. Maybe you can take from closed interval also. Doesn't matter. Okay, so you can do. Okay, you can do that one. So C1. In that case, f is differentiable, f is continuous, f prime is continuous, and then therefore f prime is continuous. Okay. So let's try to understand in this notion. So instead of f prime as a point-wise thing, that means consider then. So you want to consider not x going to f prime of x. I want to treat this as phi going to integral of f prime of phi. That's what we try to do this. Now do by, because f prime is continuous, therefore, but, so do an analysis. But integral of a to b f prime of phi is equal to minus integral a to b f phi prime. You see. And look at this one. So these two quantities are equal, but this does not require differentiability of, this does not require differentiability of f, require differentiability of f. Okay, so you can do this one. So even if f is locally integrable, you can define the derivative of f. So this motivates if f is locally integrable, define the weak derivative of f denoted by df. F prime, I look for the classical thing, and then the denoted by, so df is my weak derivative notion. Okay, so let me mark it here. By, not as a point wise. Now everything is defined. I am viewing it by this thing. phi going to, okay, df acting at phi, and by definition this one integral of f phi prime. So one of the question you can immediately, so you have the definition of weak derivative. This is your definition of weak derivative. So you're continuing, so you're making an association phi going to df acting at phi in this way, and this is well defined as f is locally integrable, defined as locally integrable. The major question you may come, or the difficulty will come, is df represented by a function? Is df represented by a function? Represented by a function. That's important, right? Otherwise df may be only an association. So what we have seen, that every locally integrable function produces an association uniquely, but there may be an association which may not be coming from a locally integrable function. You will see that. You will immediately see an example now. Is df represented by a function? So we'll give a couple of examples quickly now before going by a function, some function g. Okay, that is, if you want to identify df of phi, is that is, does there exist g locally, say locally integrable, such that df acting at phi is equal to integral g phi for all phi. That's the question. Here the question is that does there exist, here is the thing, right? Df at phi is equal to, I ought to put a minus I forgot to put a minus I. Yeah. So does there exist a question here? This double integral is does there exist, so that means minus integral f phi prime is equal to integral of g phi. That's the question. So unfortunately this is not true in general. You will see some simple example. Not true in general. In other words, the derivative of a locally integrable function need not come from a locally integrable function, need not arise from a locally integrable function. So let's see a couple of examples and stop quickly. So you can do it. Examples are exercises also. Okay, examples. So you do the computations. Examples. This you can also view it as exercises. Okay. So let's do one example. Take f of x equal to mod x is not C1. So you're looking for functions which are not C1. Okay, if it is C1, there is no issue. Okay, because you know the classical derivative in minus 1 to 1 is not C1. So you want to compute weak derivative, df, because weak derivative is defined for a very locally integrable function. Meaningful or not, we will see. So what is your df at phi? So you take phi in d of minus 1 to 1. That means phi vanishes in a neighborhood of 1 and minus 1. This is equal to minus 1 to 1 modulus of x and phi of x. and now you separate it because it's differentiable in minus 1 to 0 and 0 to 1, so you do minus 1 to 0. Then in that case, minus 1 to 0, it is minus, right? So yeah, you have to compute df at 0. Yeah, sorry, this will be with, by definition, this is minus and this is phi prime. So that's what you are, the derivative goes here. Okay, so the derivative goes here. That's what the definition. So this is in minus, it is minus x, so x phi prime of x plus integral 0 to 1, and that will become minus 0 to 1 x phi prime. Now in this it's differentiable. Now it's differentiable. So integrate by parts equal to integrate. This is the exercise, parts. Do it an integration by parts. You can see that this is nothing but integral minus 1 to 0 phi x dx plus integral 0 to 1 phi x dx. Okay. So minus maybe here minus, that's equal to that one. Please do that integration by part. So define, that's exercise, simple exercise, gx equal to, okay, minus 1 if x is in minus 1 to 0 and 1 if x is in 0 to 1. This endpoint doesn't matter. Okay. At 0 doesn't matter what we are doing. That implies your df is identified with this g almost everywhere, in fact except at the origin, and we always look for in an integration theory this one. So in this case it's a nice example. The next example is more difficult. So you define in this case, this is a very important example from the in electrical engineering, understanding the pulses and the signal moving. Okay, and this is also called a Heaviside function. If x is in minus infinity to 0 and 1 if x is in 0 to infinity. So this is called a Heaviside function. Heaviside function, and so the function is this one. This one, open here, closed. This is your h, and I would like you to compute. So this is your exercise. Immediately you can do it. So you compute your dh acting at phi. This is nothing but minus because it's 0 up to that one, 0, and phi is in d of r now in this case. Phi minus infinity to 0, and that is 1 phi prime of x. There is nothing to do this one. So the exercise is below coming, and here this is nothing but phi 0, you see. So the question exercise is that there does not exist any locally integrable function. See this exercise. I would like you to know any locally integrable function g such that phi 0, you need to do dh of e is equal to integral minus infinity to infinity gx phi x. What you do is that to prove this exercise, construct a sequence of functions such that phi k of 0 is equal to 1 and all other phi k, but it will go to more and more. So you construct a sequence of functions like this, minus 1 over k to k 1 over k. So you construct a sequence of functions like this, okay, with phi k of 0 is equal to 1, and then derive a contradiction. So work out. So you see there is a function for which phi function h, which is a, how we said, which is a complete singularity because h doesn't even have continuity, and but you can compute a, so there is you will not even know that one. So you can compute a weak derivative of this function. So it's a global concept. It's not that point-wise concept. Okay, and so that's it. So we will stop and continue and give you the definition of distributions with this thing, and we are going to give a definition of the weak derivative for all these objects, not just function. What I established is there is a class of objects, and in the weak derivative produces that. So we will introduce that in the next class. Thank you.